Hi, this is another one of my videos that I'm making for myself to remind myself of how I did things. But if anyone would find this interesting, they're welcome to watch it. Now this time, this is about recursion and whether it's a good idea in general or in certain cases, and iteration and also memoization, which I think ought to be called memoisation, but maybe something is already called memoisation. So I'm using as example the Fibonacci sequence or series, whichever it's called, which, as a brief reminder, you start off with 0 and 1, and then you add them to the two together, which makes 1, which makes 1. Then you add the last two elements together, which makes 2. Then you add 1 and 2 to make 3. Then you add 2 and 3 to make 5. 3 and anyway, that is what the Fibonacci sequence series, whatever, looks like. Useful for all sorts of things. Right, my basic program is to create it. I'm importing decorators in time because I will need them. I've got this function that says, hello, are you a positive integer? Otherwise, if you're wanting the noughth element, it's just 0, and if you're wanting the first element, it's just 1. Otherwise, you are calculating it and you're saying, right, I want to find out, I'm calling that function for the previous element and calling it for the one before that. So in this example, you come in 0, 1, yeah, then you're looking for 2. So you're actually calling it for 2 minus 1, so you're getting the first element and adding it on to the noughth element, which is exactly what I was doing up there with the 0, 1, 1, 2, 3, 5, 8. I won't go on, I'll make a mistake. And then I'm just printing out the first 15 numbers. So we'll see what that does. And there we have it. That's the Fibonacci sequence, beginning of it, 0, 1, 1, 2, 3, 5, blah, 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 blah. But for doing something that simple, that seemed to take quite a long time. So I've got a decorator that I created to see how many times this function is being called. Now the time will go up considerably because it isn't that that's taking any longer, it's that the count calls is taking time to do it, but it's just a rough approximation and we'll see what happens. Right, it is calling that function an awful lot of times. It's still going, it's still going, it's still going. Now, I'm only creating 15 numbers and it called it 3,177 times. And you think, why on earth is that happening? So if we just look at that, if you want the noughth, you just return 0. The first, you return 1. But if you want the second, you have to call the function for 0, for 1, call the function for 0. Then for the if you're looking for the third, you have to do it for 2 and 1, but then 1 you have to do it for 1 and 0. And every time you do that, it's another call, another call, another call. So when you get down to here, it's 1, 2, 3, 4, 5 calls, then it's 2, 4, 6, 8 calls. And it's ridiculous, and the problem is that you continually are having to recalculate F1, F1 and F0 aren't a problem because they're just 1 and 0, but you're recalculating F2 every single time that you're using it. And for every number, for 5, you're having to calculate 4, 3, 2, 1. For 6, 5, 4, 3, 2, 1. And it would be much better if you actually saved the value of F4, for example, because an F3. So then when you were looking for F5, you just add them together and things ought to work. I will show you what I mean. There, I've created a dictionary to store the numbers, the series in. It needn't be a dictionary in this case, it could just be an array, but I've made it into a dictionary. And then I'm just checking to see whether it's a positive integer. Now, as before, now here it says if it isn't in the dictionary, i.e. it hasn't already been calculated, when you calculate it there, you put it in the dictionary. And then you're returning the element of, the right element in the dictionary there, whether or not it was already there or you've just calculated it, if you see what I mean. Now that ought to save an awful lot of time. And I've got the count calls here, but the count calls, of course, is affecting the time. So we'll try running it. Excuse me. There you can see, by caching all the values, you only need 41 calls, which is pretty good. And that time, it wouldn't be that time really. It's be a lot quicker if you didn't do your count calls. But the problem with that is that you're taking up space with your dictionary. So it's a bit of a trade-off. The first method took a long time but didn't use up any memory, and this one is using up memory but it's quicker. There you can see, there's your dictionary. Now in the scheme of things, that isn't a very big dictionary, but you could be doing something where it is a big dictionary. So you have to think, speed, memory, don't know. But there's another way of doing this, because if you look at that, you're having to declare your dictionary and you've got your method. If you put it in a class, wherever my class has gone. Whoops. Where are we? There. This time I'm just using an array, and I haven't put in the at count calls because it would be meaningless, because all the recursion is happening there really, because it's self n-1, self n-2, so it all works exactly the same way, apart from it is an array within the class as opposed to a dictionary outside. And we'll run that. Right, that worked. That seemed to run terribly fast, but it worked. Then there is another way of doing it, which is using iteration. I may as well take that out now. Now this time it isn't taking up any memory because you aren't saving it, and it isn't using recursion, and you just say, hello, is it a positive integer? And if it's naught, it's 1. If it's the first, it's 1. If it's the noughth, it's the naught. And here you're doing it like you do manually. So you've got previous equals naught, and the fib number is equal 1. And to calculate the next one, you take the fib number, which is 1 in this case, and you shove it into previous, and then you add the previous and the fib number together, and you put it in fib number. So for example, you know, if you have 0, 1, fib number, no, previous is naught, yep, and no, not previous, sorry, fib number equals 1 there, which you put into previous, like that, and then previous plus fib number, which is 1 plus naught, you put into fib number, so you've got 1 in there. So you've now got previous equals 1, fib number equals 1. You go into it again, and fib number is 1, which you put into previous, and previous plus fib number is 2, which you put into that fib number. It's, if you see it working, it works wonderfully. And here again, we come in and you say fib number equals 2. Yup, you put that in previous, and then previous plus fib number is previous plus fib number is 3. Have I gone wrong? Anyway, you get the idea. It's just doing it exactly as you would do it manually, and then you just return it, but you aren't storing it, so no memory worries. There we go. And it's taken 15 calls to do it, as opposed to the 41 for the caching method. And there we have an array of Fibonacci numbers, but it isn't storing it. So if you want to do it again, you're going through all of that again. So this time it's taking the time, it's only taking the time that it needs to take, but every time you want to create another Fibonacci number, you're having to do it all over again because it hasn't saved anything. So I haven't heard of anyone doing it this way. This is my if I can find it, I'm calling it my partially memorized recursion version. Like that. Now again, I've got my fib dictionary like that, and I'm going to save every 7 times, which I will explain in a minute. So is it a positive integer? Yeah. If it's in the dictionary, you grab the value, otherwise you calculate it. Whoops, otherwise you calculate it, and then you're doing your recursion bit, doinky 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 doinky. But the difference, and you aren't saving every time, or you're saving every 7th time, or you aren't actually. You're you're saving your 7th and 8th time, and then your 14th and 15th time therefore you've got a nice starting point. I mean, this is very difficult to explain, but if you just look at it and see what it does, then it works wonderfully. So if I run this, right, it's taking 225 calls to do that, which is a lot more than your 41, but not nearly as many as your 3,100 whatever. And you're using up less memory because you've got your 0th element, your 1st element, your 7th element, your 8th element, and then your 14th element. And it means that when you want to go back in your recursion, you go back to the last step that is being calculated, which saves time. But 7 out of 15 is quite a big step, so you can change it. If you change it to 4, for example, far fewer calls, but you use more memory. So this way, that I will call the Swift method, because I don't think I've heard of anyone doing it like this before, means not only can you have the payoff between doing all the calculation or and save no and cache no values, or cache all the values and then you have an awful lot, it's an awful lot faster. This method means that you can customize it to your requirements, as in speed versus memory. And if you put that, if you increase that number there, the save every, your speed will go up as that goes down, but your memory will go up. Sorry, the bigger that number is, the longer the processing, but the less memory you use, and vice versa. The smaller the number is, the quicker it is, but the more memory you use. Well, it was just a thought and it didn't make any sense, so there we have it.